I'm going to continue on with this idea of curve fitting. This is the overall theme of the week. This is the idea of taking data that you have and trying to make sense of it. And curve fitting is one of the sort of the standard techniques you would do that. In the last lecture, what we did is we sort of did these approximate curves. We picked a function like a line, and it never actually went through the data, but it gave us the right trends, right? So the line we picked to sort of do this curve fit never actually went through the points necessarily. Now, what are the objectives that you're trying to achieve when you do the curve fitting? If you have a set of points, these set of points are very specified locations. Let's call them x0, y0, x1, y1, all the way to x of n, y sub n. So here we're going to have a total of n plus 1 points. Okay? Keep that in mind. We have n plus 1 points. We put them out there. And what we did before with the curve fit was to sort of draw our best fit line, let's say, through this data. Let's say this looks something like this. And the objective in drawing such a thing is that I only have data at very specific locations. Suppose this was some kind of trend curve. This was a temperature as a function of time. And these are at the different hours. Well, I could ask you, well, what was the temperature instead of at 5 o'clock or 6 o'clock where you have data? What is the temperature at 5:30? Well, you don't have a data point for it. So you might say, oh, I don't know. I have no idea. Well, you do have an idea. Your data all around you tells you something self-consistent. And so what you want is maybe I want to get a data point for you where you don't have a data point. This is called interpolation. Okay? Standard use of getting these curves. What you want these curves out for is to do interpolation exercises, for instance. This is one of them. Give me data where you don't have, give me a prediction for where this curve is, even where you don't have data. And interpolation will do this. Second, you might say, well, look, my data goes, let's say, from 5 o'clock to 12 o'clock. I want you to tell me what the temperature is at 1 o'clock or 2 o'clock. In other words, my last data point is over here, and I want you to tell me some value over here. Well, notice all my data sits in here. So this is outside of the data range. This would be called extrapolation. So interpolation is trying to give you data or give you sort of where you are in the trend in between your data. Extrapolation gives you a prediction of some place that's outside of your data. Okay? Those are the two key features that you want to think about when you start doing curve fitting. The curve fitting isn't just to produce a cool, some kind of plot that matches up. The idea is that you want to use this trend line to do something predictive or to try to understand what are the relationships that are fundamental in this curve. And so this is what allows you to do. All right. So again, if you look at what we've done here, is we've just said, I'm going to go ahead and plot that blue curve, which is a least square fit. It doesn't go through any of the data. But suppose I want to now develop methods that actually goes exactly through data points. So in other words, I want something here that might go like this. Actually, the data ends here, right? So I want a curve here that actually goes through every single data point. By the way, what is the error in this case? If this curve goes through all the data, my error is exactly 0. Because normally the way you do the error is you say, how about if I take my prediction versus the actual data point? Well, your prediction is going exactly through the data points. So how would you set up a system to actually give you something like this? So what you want to do is a polynomial fit. You have all these points. So how about you say, how about we do a polynomial fit through this data? In other words, you take a polynomial of degree n, and you fit it through your data. There it is. There's nth degree polynomial. And notice, how many coefficients do I not know? A of n, a, all the way down to a of 0. So there's n plus 1 coefficients that I don't know. And by the way, there are n plus 1 points. These are the constraints. So this matches. So I could certainly take this, plug it into those data points, and I can get some constraints and solve for the a's. In particular, what I do know about this is it has to go to the point, for instance, x0, y0. That's one of the data points. That line has to go through it. If I want it to go through, then what happens? Then you get a of n, x0 to the n, plus a of n minus 1, x0 to the n minus 1, all the way to a1, x0 plus a naught. And what's it equal to? Y naught. For the x0 values you get y naught out. So there's one equation for that data. You get the same thing if you go through y1. A of n, x1 to the n, all the way down to a1, x1 plus a0, y1, all the way down to the nth point. So there's n plus 1 constraints because I started counting at 0 and not at 1. So there's n plus 1 constraints. There is n plus 1 unknowns. I have an n plus 1 by n plus 1 system of equations that you can solve for. Okay? So that's one way to do it. So in other words, it comes down to ax equal to b. As advertised, this keeps showing up. There it is, ax equal to b, because it has to fit this. All right. So this is great. I can do this. It's rather expensive because now I'm going to have to do an order n cubed operation to get this curve fit. Okay? So whereas before, if you remember the least square fit, all I got to do is compute the matrix coefficients, and then I can solve that. And it's a much smaller system. Here the system's quite large, and the other system, because I reduced it down to 2 parameters like a and b, I solve it 2 by 2. Here I've got to solve it n plus 1 by n plus 1, which can be quite large if I've had a lot of data. And you say, well, but the advantages are that my error is 0 because now I have a curve that goes through every single one of the data points. Okay? All right. So let me tell you that this is not what MATLAB does. This is a very inefficient way to write down a polynomial to go through all your data points. The standard way is to use what are called the Lagrange polynomials. Okay? So what we're going to do effectively is write down this nth degree polynomial, but in a much simpler, more elegant way. What I mean by that is what we want to avoid doing is solving this big ax equal to b system. So let's talk about a simple example. I have 2 data points. There they are. And I want to think about, okay, so what would I fit between 2 data points? I have 2 data points, which means I'm going to fit a first degree polynomial through them. Okay? So I'm going to fit something of the form like this. And the question is, how do I determine m and how do I determine b? Well, I could certainly just plug in these values. And if you do that, you can get something like this. So let's get plugging these 2 constraints in. Here's a formula that you would get. So here's your b. And your m is this complicated, well, part of your b is also wrapped up here because you have x naught times all this stuff that would go over here. And your x is here. And your m is this and this piece. It's kind of complicated. Let me suggest a simpler way to write this. What do I want this line to do? I want this line to go through this point. I want this line to go through that point. So I'm going to write down a first order polynomial the following way. And you'll see how efficient and nice this is. And it doesn't involve me solving a 2 by 2. I can write this down without actually solving the 2 by 2 system of equations. I can say, look, how about a formula like this? By the way, this is the simplest Lagrange coefficient formula. Here's how it works. What I want to do is say, write it down like this. I want it to go through at x0, y0, and at x1, y1. So I've written out the two x points here. And then what happens with these functions? Well, let's plug in x0. So at x0, this thing should be y0. If I plug in x0, oh, first of all, look what happens over here. If I plug in x0, I get x0 minus x0. This is 0, so this is gone. If I put x0 here, I get x0 minus x1, x0 minus x1. This is 1. So if I put in x0, I get y0, because that's 1 and a 0. If I put in x1, notice that I get x1 minus x1. That's gone. That's 0. And then I get x1 minus x0, x1 minus x0. That's 1. I just get y1 out. This function works. I didn't even have to write down any kind of formula for it. In fact, one generic way to think about this is to write this as the following. The y of k's, in other words, your y values you're going through, times this coefficient here. These are called the Lagrange coefficients. Okay? And in this case, the Lagrange coefficient is either this one here or this one here. And the whole purpose of constructing these Lagrange coefficients is that the Lagrange coefficients are either going to be 1 or 0 at the data points. That's it. They either take on the value of 1 or 0. And by the way, they only take on the value 1 at one of the data points, wherever this k is. So at 1, if x of k, this is going to be 1, it's going to be 0 everywhere else. Okay? So this is going to be an important property that we can use. And in fact, the important thing about this is I can write this down ahead of time. I don't have to go solve an n-by-n system. So let's contrast the difference here. What I'm trying to construct here is a very general way that I could write down, you give me the data points, and I just can write down the formula for you immediately without having to solve any set of equations, versus over here. And the philosophy is I've got to plug in every data point to write down a giant ax equal to b system. And this is going to cost me order n cubed to solve. So I've got to actually go solve this. I've got to not only plug it in, I've got to go solve it. This is this way. That's sort of straightforward. I would call this the brain dead way. You're going to do, you would think about doing this right away, but then it's just not very efficient computationally. In fact, nobody does this in computing. What they would do is something like this, where you can say, hey, look, I can very generically construct an nth degree polynomial just by trying to write down these Lagrange coefficients so that they're either 1 or 0. In fact, let's write this down for an nth degree polynomial. So here it is. So now if I'm going to fit it through the n plus 1 points, and what I want to do is fit an nth degree polynomial. And what I'm going to do is write it as 0 to n, the y of k's, ln k x. So here are my y values of the data. Here are my Lagrange polynomial coefficients. And the question is, how do I make these up? Well, let me write down the formula for them, and we'll walk it through to make sure you feel comfortable with it. ln of k x, which I can define at the beginning of my code, is the following. xk minus x0, xk minus x1, xk minus x of k minus 1, x of k minus x of k plus 1, all the way to x of k minus x of n. And on the top, I have x minus x0, x minus x1, x minus x of k minus 1, x minus x of k plus 1, x minus x of n. Okay, that looks a little bit complicated, but notice how it's going to work. Let me show you some examples of how it can work. This function here, I'm going to argue, is the following. Will equal 1 when j equals to k and 0 otherwise. Or j is not equal to k. Let's just show that. If you put in j equals to k, okay? So in other words, when, when for this thing here, n k x of j, okay? So I put in x of j, okay? And let's look at this thing when this j is k. So if I put this in here, let's look at when I put in when the j is equal to k. So when the x is x of k. When it's x of k, what do I have on top? I get on top x of k minus x naught. But wait, I have one on the bottom. The one on the top and the one on the bottom cancel. Gives me 1. And then I have x of k minus x of 1. Wait, I've got an x of k minus x1 on the bottom. Cancel. In fact, they all cancel. All the way down to here, where I get x of k minus x of n. I have x of k minus x of n on the bottom. This is 1. Now, let's suppose it's something else. When it's not x of k. Well then, what's going to happen? Well, in that case, this whole thing here is if you start putting this thing in, you're going to get a 0. Suppose, in fact, that the x of k is not the j. Suppose the k was like 5. And now we're going to say, oh, you know what I want to do is I want to plug this in and evaluate this like at when k equals 0. Put an x of 0 in here. What do you get? Oh, x of 0 minus x of 0, 0. The whole thing's 0 then. If I put an x of 1, the whole thing is 0. If I put an x of 2, it's all 0. In fact, the only thing that's going to make this thing non-zero is if I put in the k. Otherwise, it's 0. And it's by construction. I did this on purpose. Not me. Well, the people who made this up did this on purpose, right? The whole point of this is, what do I have to do up here so that everything, it's always 0 except for when it's x of k. So it's not 0, and then that it would be 1. And this is the formula for it. This is your Lagrange coefficients. This is a nice thing. You can program this into your computer very nicely. And notice, you're not solving an n by n system or an n plus 1 by n plus 1 system. You're just saying, look, there it is. There's the formula. I can just calculate everything. I have the formula directly. I don't have to do anything else. So if I want to evaluate this polynomial, there it is. Okay? So that is the Lagrange polynomial coefficient formula. And this thing here will go through all your data. Okay. Let's talk about some problems with this. I hate to bring up problems, but it's important that you understand why you know, what might be some issues here. Something to notice. When you do this reduction method in the last lecture, we talked about let's do a curve fit using least square fit. In other words, I pick a function ahead of time. I say, I just want to fit a line through my data. I don't really care that it's not quite going through all the points. I just kind of want to get a trend line out. It's great. Stuff works pretty nicely. You can pick a line, a parabola, exponent. Here, this actually has 0 error because it goes through every data point. So you can say, well, why would you use the other method? Why would you do the line fit when you could just do this? And let me tell you why. And this is actually sort of the Achilles heel of doing a polynomial fit to data. Okay? So it's not just about this method here. This is just the fact that you have all this data and you want to do a polynomial fit to it. So let's take a bunch of data. Okay? What do we know about polynomials? Okay, let's do a first degree polynomial. It's a line, right? This is ax plus b. Second degree polynomial, what is it? Parabola. Third degree, what is it? Something like that. Fourth degree. W, Huskies. Okay. Fifth degree. Okay, so you see what happens here? As you keep going up in degree as a polynomial, you get more and more terms. In fact, how many turns do you get? For n equals 2, you have 1 turn. N equals 3, you get 2 turns. N equals 4, you get 1, 2, 3 turns. In other words, it goes down, up, down, up. Generically, that's what it looks like. Here you get 1, 2, 3, 4. So in other words, whatever the degree of polynomial is, I have n minus 1 of them turns. Okay. What if I had like 20 data points? Actually, let's do the following. If I have 21 data points, then what I would have is a 20th degree polynomial, right? So I would have p20x to fit through all these data points. How many turns does the 20th degree polynomial have? 19. So I've got to do this 19 times fitting through this data. But if you look at this data, and if you ask me to draw a nice line through it that goes through all the data, I would do this. I would say, oh, look, I want something smooth and nice. Okay, I kind of missed that data point, but this is awesome. You could just kind of do that. Oh, there it is. Okay. There you do. You'd have something like this. But it turns out this really doesn't have 19 turns. And this leads to the phenomena called polynomial wiggle. I didn't make that up. It's true. Look it up. Polynomial wiggle. What is it? It's the fact that this thing here is having to do 19 turns in this. And so what happens is it actually does a very good job in the middle. In fact, let me do it in blue. Here's what it would look like, maybe. I'm making it up. We'll play around with it tomorrow, on the third lecture of class of this section. I'm going to go through some code that shows this. But this is the phenomenon of polynomial wiggle, which it does really well in here, but it didn't take enough turns. It's got to take 19 turns, and then it saves it all up for the endpoints, and it just takes these huge excursions. You can see this. There's actually a plot of this in the notes, figure 3.2 in the text. And this is a problem, because if you are looking over here and here, so maybe, yeah, the data looks fine in here, but if I say to you, interpolate for me some value. In fact, I want to know the value that you don't have data for. I want you to extrapolate a value for me right there. It'd tell you, with this polynomial fit, that that's where things are, which is complete garbage. The polynomial wiggle makes you distrust this technique. So although you can technically fit things, the polynomial wiggle can in fact be a deal breaker. Because if you have a lot of data, this thing's going to suck. Okay? So just keep that in mind. If you don't have that much data, then maybe it's not so bad, right? You're not taking so many turns. But typically, if you have a lot of data and you put this polynomial through it, you're in trouble. It's going to do a very bad job for you. Okay? Okay, so that is one way to think about data fitting. Another way to think about data fitting. In the first lecture, we talked about data that actually just kind of gives you the right trends. It actually doesn't go through any of the data. You have some error, but it does a nice job. These least square fits. Here, this is a polynomial that goes through all the data. So the error is 0, but clearly very bad predictions. So again, the error is 0 because it's going through the data itself. It's just that it's going to give you a very bad extrapolation and interpolation results. And remember, the only reason you're doing data fitting is to get yourself something you can do extrapolation and interpolation. So if it doesn't do a good job giving you good extrapolation and interpolation, you're in trouble. Okay, this leads then to a final consideration of how to do curve fitting, which is called the method of splines. And by the way, splines are quite great. Splines are one of the more heavily used tools in animation. So splines allow you to sort of fill in details and give you a very nice interpolation of data in a smooth way, unlike what you saw here with the polynomial wiggle. So let's talk about what splining is all about. So let's go back here to some picture, some data. And suppose actually I really want a curve that goes through that data, really goes through the data points. I don't want all this polynomial wiggle crap going on. So what I could say is, look, I want something going on here, and what I really would like to do is see something like this. If I were to draw something that goes through this, maybe you do something like this, where it's nice, smooth, goes through all the data. Let's talk about smoothness. How do you measure smoothness of a function? Typically, we think about the derivative tells us the rate of change of a function, or the smoothness. And so if we want something smooth, what we'd like is you know, something's going to be involving the derivatives of the function itself. So I'm going to tell you the main ideas of a spline. A spline doesn't try to construct something over the whole interval. A spline says, OK, let me look between here and here. Let me put a function in there, just in that little segment. What I'm going to do is construct a cubic function in there. I'm going to call this s of k, x, which will be the following. All right. So what I've written down for you here is a cubic, right? This is a plus bx plus cx squared plus dx cubed, but in a slightly different form. I've written this for, let's say, the kth interval. So let's actually repoint where this is. You know, maybe there's a kth interval that goes from here to here. And I'm going to write in that interval, this is going to be the kth interval. Okay? So I'm going to go from the x of k point to the x of k plus 1 point. And I'm going to define in that region between x of k and x of k plus 1 by this function here. Okay? Now notice, when I'm at x of k, that's 0, 0, 0. All that drops out. And so this thing here tells me the value at x of k. And then this is going to go over to this point. Now at this point, I'm going to do another spline from x of k plus 1 to s of x, from x of k plus 1 to x of k plus 2. So I have a cubic here, cubic there, cubic there, cubic there. There's these little cubics everywhere that I have this. So by the way, let's contrast this with a method you know very well from childhood. If I were to do the same exercise and tell you as a child, hey, okay, go ahead and do something here, what you would do, because we have all these little drawing books to do this, you would do connect the dots, right? In fact, I loved those connected dot books when I was a kid. You could like do stuff like this, and out comes Santa Claus, right? So you get this connect the dots. But here's the interesting thing about this. Does that look smooth to you? If the dots are very close together, it would at least appear smooth to you, but they're clearly not. What's the deal? What's the derivative here versus here? Right away, that's the suggestive piece to you. The derivative here is this way. The derivative there is that way. You have a mismatch in the derivatives at every single data point. This gives it the look of choppiness, right? The connect the dots. So notice when I drew this over here, what did I do with my hand? I kind of just drew this nice smooth curve all the way through all the data. So this is great. When you're a kid, you don't, well, as you get more sophisticated as a kid, you start seeing the picture that you need to see, and you might start smoothing out your connected dots. But at least when you're a kid, you just go from 1 to 2, 2 to 3, 3 to 4, right? You just draw straight lines. And what you end up getting is something that looks fairly choppy, okay? So by the way, if you remember when we did plotting, this is the default in MATLAB, is that when it's going to give you a function to plot, it's just going to do a connect the dots between points. You can do better. You can spline this. Okay, so how do we think about constructing a spline? I've given you an equation. At every single cell, I have a cubic. Okay, so let's talk about then how you might connect these cubics together. In here, you're just drawing a line, right? This is just, you just draw the line. This is just y equals mx plus b. You draw that line, you draw that line, draw that line, draw that line. To make this smooth, I want to have relationships between here, my neighbors. The big thing here is notice when I have a smooth curve, the derivatives match. At least that's one thing to start thinking about. I'm going to even do one better. I'm not going to make just the derivatives match. I'm going to make the second derivatives match as well. So the first derivatives match, second derivatives match. The function is continuous, and that's how I'm going to start constructing a spline. Okay, so let's leave that concept there. Let me come over here, erase this board, and then we can start building the spline. Okay. So, what do we want to have happen? We have this function, s of kx. We want to build it. We want to figure out how do I build it? Because after all, let's come back over here. These are easy, but I don't know this. I don't know this. I don't know this. I don't know this. So I have 4 unknowns. Now, I already showed you that if this thing goes to this point here, then in fact, x of k, at x of k, that's 0, 0, 0. Oh, so the only thing left over is sk0. So at s of k, x of k, I have sk0, and this thing better go through the point. So sk0 is y of k. Great, so at least I know one thing. But there's still 3 things I don't know. There are 3 unknowns. 3 unknowns for every single patch that I have. Okay? So the question is, how am I going to go solve this, right? I mean, how do I impose some constraints on here to pin down what these things should be? So let's start building this. So first of all, I want s of k, when you evaluate it, at x of k, the left boundary point, to be y of k. And by the way, let me draw some points here. So this is going to be my x of k point, x of k plus 1 point. They don't have to be evenly spaced, by the way. I'm just drawing it for, and this is at value of y of k minus 1, y of k plus 1. So remember, I'm defining now, right here, this s of k is in this interval. It's in the interval, so it's s of k is defined in an interval where x goes from x of k to x of k plus 1. Okay? So first of all, I want this function in this interval to go through this point. Second of all, I want it to go through the other point. I want it to be here, and I also want it to go through there. It's not too much to ask, is it? Go through here, go through there. Hit the points. So So take this cubic function that I have, go through this point. If this is defined in this interval, it has to go through here, it has to go through there. Two constraints. By the way, every constraint I add, right, that's another equation that I impose, which means that's another equation that has to be satisfied, which gives me equations to determine these coefficients of the cubic. These two constraints have to be satisfied in that interval. Those are two constraints. And how many unknowns do I have in that interval? 4. So I still need two conditions. All right. Here's what else I want. Smoothness is related to derivatives. If we learn nothing else from connect the dots, it's this discontinuity in the derivatives that makes it look choppy. So what I want to do is impose some kind of smoothness condition. So here's what I'm going to do. The derivative let me write this down. So let's come over here. At this point right here, I calculate the derivative. So here it is. I have my function s of k in here. And by the way, over here, I have a function s of k plus 1 in the next interval over. So what I want is, over at this point, I take this function, I go over to this point here, and I calculate its derivative. Find the derivative, s prime, at x of k plus 1. And I want the derivative to be equal to the derivative of s of k plus 1 at x of k plus 1. In other words, take this function, takes its derivative there, take this function, its derivative there, make a match. Impose that constraint. The whole goal here is to make it look smooth. Not only going to do the first derivative, I'm going to also do the second derivative. So I don't just impose that the derivatives match. I impose that the second derivatives match. In other words, the inflection point has to match. Not the second derivative, which often is related to sort of inflection ideas, they have to match. How many constraints do I have? 1, 2, 3, 4. How many unknowns in this interval? 4. But these 4 here are connected to these 4 there. How are they connected? Because of this derivative condition. Okay? So I get a big, large system of equations to solve because I can't just solve this by itself. I can try to solve this, but then it's connected to the coefficients here, which are connected to the coefficients there, and so forth and so on. So this looks great. This gives me a way to start thinking about how to construct these splines that make it look very smooth. Now, where does the problem come? And you're going to get, again, when you do all this, because they're all connected, you're going to get a giant ax equal to b. Now, here's the problem. If I take all my data, so I have some way to do this. These points connect to here, so forth. Hey, but what about at these endpoints? This is a problem because if I start doing an equation count, I run into problems. So first of all, how many points are there? Remember, I start from point x0, x1, all the way to x of n. So there's n plus 1 points. All right? So first of all, let's talk about this constraint right here. This constraint here gives me n plus 1 equations. Right? It has to go through every single point. That's what this thing says. So it gives me n plus 1 equations. Now, continuity, which tells me that one has to connect to the other. In other words, this has to connect to the other side. Well, now, so this is great, except for what happens on the boundaries. You know, so when I define this guy here, he's supposed to connect out. What I end up with is a problem here. When I try to match, this connects to this. This connects to this. Who is this guy connecting to? And who's that guy connecting to? So when they each connect together, this continuity says this guy connects to this guy. That's a constraint. This connects to this. That's a constraint. But there's no constraint imposed here or there. So this constraint, we call it here, of S of k matching up to S of k plus 1, there's only n minus 1 equations. And by the way, that's also true for the derivatives, because you're trying to say, let's match derivatives, and let's match second derivatives. Okay? So I have n minus equations here, n minus 1 equations here, n minus 1 equations there, n minus 1 equations there, but n plus 1 equations there. How many unknowns do I have? Well, I have n plus 1 points, right? And I have, so that means there's n intervals. I have n intervals, and in each interval there's 4 unknowns. So I have 4n equations, or sorry, 4n unknowns. And this is going to, if you count them all up, I have n plus 1 constraints here. And remember, the derivative matching and second derivative matching and continuity, who are you matching the derivative with here? Who are you matching the derivative with there? There's no neighbor to match a derivative. So you get less, you don't get a constraint on this one or this one, or on the second derivative. So if you count up all these, you have 4n unknowns, 4n minus 2 constraints. So you're underdetermined. You have this many unknowns. You have that many unknowns minus 2 constraints. So the possibility exists of an infinite number of solutions. So that's something you should know about splines. Typically in splines, what they might do is they say they have to impose 2 more conditions. Oftentimes, one of the standard ways is to say, how about on the ends, we'll make the second derivatives 0. If I make the second derivative here and here 0, that gives me 2 more constraints. And then I have 4n unknowns, 4n constraints. And then I have a system that I can solve for these splines with. That's just one way. In fact, there are different kind of splines, and part of these splines, some of the differences really have to do with how you impose the different boundary conditions. Splines are powerful. I love splines. Reason I love splines, they're a smoothing property. They're great data fit. They look fantastic. They give you a nice smooth fit to data. And in fact, like I said, the splines are kind of like the bread and butter of the computer graphics community. Because what you can do now is you can make a shell of a face, nose. Oh geez, you connect dots and then there's your rough face, there's your eyes. And maybe you're going to do some computer graphics where you're moving someone's face around and you're only keeping track of these points. But then when you want to render this in full nice smoothness, what you do is you put a spline on it. Because what the spline is going to do is say, instead of just giving you connected dots like this, it's going to give you, that looks kind of scary actually. All right, well, it's going to give you nice smoothness like that. All right. Okay, that looks like a hockey mask. And if I do that, then it's like Halloween, which might be around the time you might watch this. So anyway, splines are great. You should keep this in mind. This is what they do. Cubics in between, and matching of first and second derivatives. And it's another data method. And we'll demonstrate this in the next lecture.